situation here. So here's what I have going on. I have a light string represented by the red line that's tied to a heavy string represented by the blue line. Now what's going to happen is when I hit play here, you're going to have this wave that's traveling in the light string that's going to travel along the way until it encounters the heavy string, and we're going to go ahead and watch what happens. Here we go. Now there should be a few things that you notice here. First, did you notice that when this wave hit this new medium, when it went from the light string into the heavy string, right here, you had this place where part of it went through into the heavy string, but part of it got reflected and was going back through the light string. So that's one thing that you should have noticed. Another thing that I want you to notice, we're going to watch it one more time, and I want you to pay attention to what happens to the wave length, what happens to the length of the wave when it goes from the light string into the heavy string. And then can you also pay attention to what happens to the wave speed, what happens to how fast it's going in the light string versus how fast it's going in the heavy string. So we'll see this again, and hopefully it's not too laggy so that you can see it all right. Here we go. Okay, and there it is. And what you should see there is that when the wave goes from the light string into the heavy string, you should see the two things happen. First, the wave slows down pretty substantially, but you should also see that the wave length gets pretty shorter in comparison to the first wavelength. So we are going to talk today about what happens when a wave transfers mediums. We're talking today about wave transmission, wave reflection, and wave interference. Now, the first two of these topics, wave transmission and wave reflection, have to do with what happens when a wave encounters a new medium. And this third topic here, wave interference, has to do with what happens when a wave encounters another wave. We're going to start by talking today about wave transmission and wave reflection, and then we'll end class today by talking about wave interference. Let's start off with first talking about wave transmission. What you just saw in this video is you saw a very light rope, and here I'm going to clear this out here. You saw a very light rope that was connected here to a much heavier rope. And here we're going to change everything. It's going to be awesome. Yes, perfect. We're nailing it. Okay, and killing the game. Okay, so what you saw here is you saw that you had this very light rope that was connected to this heavy rope here. And you saw that a few things changed. The first thing that I want to pay attention to is as the wave passed from the light rope into the heavy rope, the speed, wow, and we are particularly laggy today. Come on, Google Chrome, let's get a move on. You saw that the speed of the wave changed. In fact, what you should have seen is that the speed of the wave decreased. The speed of the wave decreased as it went from the light rope into the heavy rope. You also saw something happen with the wavelength. You saw that the wavelength also decreased. And lastly, you should have seen something with the frequency. Now, I say you should have seen something with the frequency, but actually it was very, very hard to see frequency on this simulation here, so we're going to go back and explain what you should have seen with the frequency, but this simulation really does make it very challenging to actually see that happen. So let's start by talking about speed. Now, here's a formula that you don't really need to know for the class, but it's a formula that you need to understand for the class. And the formula that you need to understand is this formula. It's a formula for the speed of a wave in a rope. Again, very specific formula. The formula for the speed of a wave in a rope is that the speed of the wave in the rope equals the square root of the force of tension in the rope divided by the density in the rope. Now, you don't actually really need to know this equation other than you need to understand this concept, that the density of the rope matters for the wave speed. And here's how it matters. Notice that these two variables are inversely proportional to each other. So if the density increases, the speed decreases. And if the density decreases, then the speed increases. Now, here's why this should make some degree of sense to you, is because density, as you know, is really just mass per volume. And the more mass you have, the more inertia you have. So if you have a higher density rope, like if you increase the density here, increase that mass, more mass means more inertia. And if it has more inertia, the rope or the wave in the rope is going to move much slower. Imagine that I walked up to a very, very high density, very massive rope, very inertial rope, and I said, hey, I'm going to put a wave through you, and I'm going to need you all to move side to side very quickly. The rope would say, excuse me, are you for serious? I have a lot of mass. I have a lot of inertia. I like to resist acceleration. I don't think so. And the wave would move very, very slowly through that very high density rope because it has so much inertia. It takes so much to get to move it side to side. But if you went up to a very light rope, a very low density rope, very low mass, has very little inertia, you say, hey, very little inertia rope, I need you to carry a little wave through you. Rope says, yeah, for sure, no problem. We can move side to side. We don't care that much about acceleration. Not that big of a deal to us. You put a little wave in a little low inertia rope and it just goes brrr, and just kind of zips on through. Nice and easy. So you can see that how much mass something has specifically relates to the speed of the wave in that rope. If it has a lot of mass, you're going to have a much slower moving rope, so you got a much slower moving wave. And then if it has very little mass, then the wave can zip on through. You can see why when we go from a low density rope like this red rope to the high density rope like this blue rope, the speed has to decrease because it's going from something with very little inertia to something with lots of inertia, and it's very, very hard to get that thing to move a lot. Now, what we're going to talk about next, we're actually going to skip wavelength. We'll come back to it. Don't worry. We're going to talk about frequency next. And here's what I want to talk about with frequency. It's very, very hard to tell in this simulation, but I think we can talk it out, and it should be able to make some... Oh, my. We are just like laggy central over here today. Everybody doing okay? You following along okay? Everybody good? We should be able to talk it out and still make some sense of it. Okay, so here's what we've got. Here's the idea. The idea is... if I send one wave, come along, buddy. If I send one wave into this end of the rope, then I should expect to see one wave enter into the blue rope. If I send two waves into the red rope, I should expect to see two waves in the blue rope. Wouldn't it be so crazy if I sent one wave into the red rope and then you look over here and two waves show up in the blue rope? You would say that is magical. Where did that extra wave come from? You only sent one into the red rope. How'd you get two in the blue rope? That's crazy. If that happened, we'd all need to start investing in ropes. Because for serious, that could totally revolutionize the whole world and the whole way that we do everything. We would have to call it the rope revolution. But no, that's not what happens. You put in one wave over here per second, and you get out one wave over here per second. If I put in 3 waves over here, 1, 2, 3 waves over here in a second, then you would expect to see 1, 2, 3 waves in a second come out on the other side. Likewise, if I put in 1 wave over here, and you saw 0 waves come out over here on the blue side, you would start to say, what happened? Where did that extra wave go? Here's the deal, people, is that waves don't just pop in and out of existence. That's not how waves work. Waves have to come from somewhere. You put in 1 wave over here, you get out 1 wave over here. That has to be true. And so, because of this principle, it has to be true that the frequency stays the same when you go from one rope to another rope. In other words, the number of waves per time has to stay the same because waves don't just pop in and out of existence. So your frequency stays the same. Oh, wow. I just realized I spelled decreased wrong. How embarrassing. Oh my gosh. This is where video editing would be oh so helpful. Okay, here we go. Moving on. Now that we've talked about frequency and speed, we have everything that we need to talk about wavelength. This equation that you see right here, this is the equation for the speed of a wave in a rope. It is a very, very specific equation, but you actually have a much more general equation for the speed of a wave. We learned it yesterday. It's V equals lambda, or V equals the frequency times the wavelength. What we see here is that V and the wavelength are directly proportional to one another. I want you to check this out. If the speed of the wave decreases when it goes from a lighter medium into a heavier medium, so speed goes down, but the frequency stays the same because waves can't pop in and out of existence, then the wavelength must also decrease in order to keep this equation true. If V equals delta x over delta t, and frequency is the number of waves that you see pass you by in a certain amount of time, and the frequency is staying the same, what that means is your delta t per wave is staying the same. And if your delta t per wave is staying the same, but your V is getting way slower or way faster, then how much ground that one wave covers has to change. If your V is getting way slower, then you have to decrease your wavelength because that wave is not covering as much ground in the same amount of time. So, you can see here that when this wave goes from a light rope to a heavy rope, the speed decreases because the density of the rope matters. The wavelength decreases because it has to be true that the wave is covering less ground in the same amount of time, and the frequency stays the same because waves can't pop in and out of existence. Here's what I want you to do. I want you to try this problem. Suppose that instead of sending a wave from the light rope to the heavy rope, suppose we flipped things around here. And suppose instead I decided to send a wave this way from the heavy rope into the light rope. Can you please then answer what would happen to the speed of the wave when it went into the light rope? What would happen to the wavelength of the wave when it went into the light rope? And what would happen to the frequency of the wave when it went into the light rope? Try answering those questions. Okay, and now we're ready to talk about reflection. When you looked at the simulation, you saw that two things happened. First, when the wave encounters a new medium, part of it makes it into the new medium, but part of it doesn't. Part of it starts heading back the other way. This is what we call a reflection. It turns out that anytime a wave encounters a new medium, part of it is reflected and part of it is transmitted. What we're going to do is we're going to start talking about the reflection portion of the program now. When a wave reflects off of a new medium, especially when we have these rope kinds of situations, you really have two types of situations that a wave can encounter. The first type of situation is a wave can reflect off of what we call a fixed end. A fixed end means that when the wave gets to the end of its rope, or to the end of its string, or to the end of its medium, there's really not a lot of flexibility or movement there. I'll show you what it looks like. It looks something like this. You got a wave that's in a rope that's traveling in a direction, and the end of that rope happens to be tied to a wall. When the wave gets to here, there's really no up and down sort of motion that can happen here. It is pretty rigidly tied to that wall. This is what we call a fixed end. It really has no freedom to move up and down. When it gets here, it's just stuck and it bounces back off. That's the first type of reflection that we'll see. The second type of reflection that we'll see happens with what we call a free end. Sometimes you'll see it called a loose end. But what you'll see here is that you'll have a wave that's traveling in a rope, and then that rope, here's the most stereotypical classic example, is that rope is tied around a pole with a nice loose knot here. And that allows the rope, when this little wave gets to the end here, that little rope will be able to move up and down here, so you have a nice free flexible end that has some motion to it. That's the difference between a fixed end and a free end. Let's look at an example of what happens when a wave encounters a fixed end and an example of what happens when a wave encounters a free end. We're going to take a look at another simulation here, and this is a simulation that we actually already saw yesterday. Here we have a wave on a string. Now, yesterday when you saw the simulation, we had no end here. It was just going out a window. But today what we're going to do is we're going to put it on the pulse mode, and then we're going to start by giving it a nice fixed end here. So now the end is nice and clamped down. It has nowhere that it can go. And what we're going to do is we're going to send a little wave pulse through. When we send this little wave pulse through, you can see here, and I'm going to change our settings a little bit so that you can see this just a little bit. Let's increase our amplitude. You can see that the wave hits here and then reflects back the other way. Check it out. Notice, every time that the wave reflects back the other way from a fixed end, oh, whoa, now I sent 2. Wow, that is just crazy banana pants. Every time that the wave reflects back from a fixed end, that wave is inverted. Did you see that? It starts by going this way and it starts going upright, but then it gets here and it hits the fixed end and it comes back as a trough. It got sent out as a crest, it comes back as a trough. Now, when we see a wave that hits a fixed end, anytime that happens, it turns out that it will always be reflected, inverted. In other words, if it went in as a crest, it's going to come back as a trough. If it went in as a trough, it's going to come back as a crest. Let's look at what happens when we have a free end here. If we have a free end, we'll change this here to what it says, a loose end. It's a classic example of you got a little rope tied around a little pole, it can go up and down. Let's go ahead and send out a little wave pulse here. Okay. And here's what we see. Let's go ahead and pause it. You see that when this wave gets to the free end over here, it is reflected again, but when it's reflected, this time, it is reflected back upright. Watch it one more time. It hits the other end and comes back the other way. It starts as a crest and it comes back as a crest. In this sort of situation, anytime we have a free end, the wave is reflected, but it is not reflected inverted, it is reflected upright. It's reflected back upright. In this simulation, it's really fun to see. You can see that when it hits the free end, it's going to get reflected back upright, but then over here, this acts like a fixed end. So when it gets reflected again, it comes back upside down. Check it out. Then when it hits the free end, it comes back again upside down, like so. When it hits the fixed end, it gets flipped, gets inverted, and comes back up right side up. So here's what you should be able to see is that anytime you have a fixed end, the wave gets reflected upside down. Anytime you have a free end, the wave gets reflected upright. That's a little bit about wave transmission and wave reflection. Next, let's talk about wave interference. And for this, I'm going to pull up a whole new page. Huzzah. Let's talk about wave interference. Now, when we talk about wave interference answers the question of what happens when a wave encounters another wave. And we're going to start by looking at a nice little simulation here, once again, of what happens when waves interfere with each other. Now here's what I have is I have 2 faucets that are sitting over a big pond. Now here's what you need to know about the simulation before we hit go, is that this kind of like bluish gray color, that is going to mean no waves. What you're going to see right now start to happen is you're going to see waves form in the pond because I'm going to hit both of these faucets and the faucets are going to begin to drip. When the faucets drip, they're going to create ripples in the pond that go outwards. Let's go ahead and see it right here. Okay, here they go. Now here's what you're going to see here. First, the places where you have these blue patches right here, the bright blue patches, those are crests. The places where you have the dark patches, those are troughs. So you can see as we hit play, we can watch it go for a little bit, this really interesting pattern develops where you have 3 like weird cone shapes that are traveling outwards. Then you have these weird fuzzy patches of gray in between them. This is what we call an interference pattern, and it's a result of waves interacting with other waves. In other words, the waves from this little ripple interacting with the waves from this little ripple. There are two types of interference, and both types of interference rely on a principle that we call the superposition principle. Here's what the superposition principle says. It says that if you had like one wave like this one and another wave, say like this one, and those two waves ended up in the same place at the same time. Actually, let's do two similar waves. Let's do this because this makes it very easy. And those two waves end up in the same place at the same time. Well, if you just had this little wave and this little wave was the only guy there were no other waves, this little wave would make a little particle move up by this much. If you just had this little wave there and the other little wave wasn't there, this little wave would make a little particle move up from the equilibrium position by about this much. But if you had both waves there at the same time, the first wave will make the particle move up by this much, the second wave will make the particle move up by this much, and all together they'll make the particle move up by this much, and then by this much. So the particle will move up a total of this much, and the resultant wave will look something like this. Except that my end was bad, so let me fix it. The resultant wave will look something like this. Something like that there. In other words, if you have two waves in the same place, you can add their amplitudes together to get what the resultant wave would be like. This is what we call interference. When one wave interacts with another wave, the two waves, you can combine their amplitudes to find the wave that results from those two waves. Let's take a little bit of a look at two different types of interference patterns. The first type of interference that you could see is called constructive interference. Constructive interference, I'm going to erase the superposition principle here. You can say bye, superposition principle. Peace out, TTYL. Okay. First thing that we're going to talk about is constructive interference. Constructive interference happens when two waves are at the same place at the same time, and they're at the same place at the same time with, oh no, why would you do that? That's so sad. Now I have to start over. Okay, here we go. Yay. Okay, constructive interference happens when two waves are at the same place at the same time, and they have their crests lined up with each other's crests, their troughs lined up with each other's troughs, and crests lined up with crests, center points lined up with center points. Everything is lined up. The resulting wave that occurs when you have these two waves in the same place at the same time is going to be a wave that one of them makes the particle go up this much, the other one makes the particle go up this much. Together they make the particle go up and down this much. So in a constructive interference type situation, you get a wave that has a way larger amplitude than the amplitude of both of the waves that created it. This is constructive interference. Let's take a look at destructive interference. Destructive interference when you have one wave that looks like this, that is at the same place at the same time as another wave that looks like this. Ooh, wait, but let me do it better. Beep, doop, doop. Okay, perfect. These two waves are in the same place at the same time. Except I've decided now that I've drawn them both perfect and they look lovely that I actually want to change them. So let's say that one wave is slightly bigger than the other. Let's do this one here, and then we'll do this one here. It's so perfect. Yes. Okay, great. What happens when you combine these two waves? Well, the superposition principle says that you can add the effect that this wave would have on a particle to the effect that this wave would have on a particle. This wave would make a little particle go this far up into the air. This wave would make a little particle sink down this much. when you combine those two, you're going to get a much smaller wave than this one because this wave is going against this wave. They'll work against each other. And the resulting wave will be something kind of like this. Something kind of like that. Notice it's this wave minus this wave because they're inside out of each other. They're undoing each other. This is called destructive interference, and the resultant wave is smaller than the incident wave. Notice though, this wave started out as bigger than this wave, and so when it comes down to it, that wave shape is going to win, and the resultant wave is going to look a lot more like the top wave than it does like the bottom wave. This is an example of destructive interference. You can also have something which we call complete destructive interference, which is what happens if you have a wave that looks like this and a wave that looks like this here. Oh gosh, let me fix it. Sorry for my perfectionist tendencies. And a wave that looks like this. You combine these two waves. Well, these two waves are crazy similar to each other. In fact, if you had two waves that had the same amplitude, but they were just perfectly out of phase with each other, in other words, all the crests were lined up with all the troughs and all the troughs were lined up with all the crests, if that happened, then you would have this, no wave. Because this one would try to make the little particles go up, this one would try to make the little particles go down, and in the end you would have no wave whatsoever. Let's go back to that simulation that we saw. In this simulation, you see that we have here these two waves, this crazy wave pattern sort of situation. The first thing that you have is you have this band right here. And this band right here in this little triangle, you have constructive interference, where this wave has interacted with this wave, and together they've made a deeper trough and a steeper crest. This crest is higher here than either of these crests are on their own. Then these troughs are deeper than either of these troughs are on their own. Then you have this weird patch right here, these weird lines of grayness. And those weird lines of grayness, if you remember when we started the simulation, the grayness means no wave. You have this patch of no wave and this patch of no wave right here. That's because the two waves have destructively interfered with each other. And as a result, you have these weird patches where there are actually no waves whatsoever. This weird looking pattern is what we call an interference pattern. And it's actually kind of like how we found out that light is a wave, is because we saw that light makes interference patterns. But more on that later. This is a little bit on interference. Now what we're going to talk about next is one very specific example of a very specific type of interference that can happen. And that's the interference that's used to create a standing wave. Now I'm going to make a new drawing here, and we're going to talk about standing waves. Now standing waves are really just a result of constructive and destructive interference. And to show you a little bit on standing waves, I am going to show you a simulation here. Now, I did have this simulation already pulled up and ready to go, but then my computer accidentally restarted itself while I was in the middle of recording this video the first time. So now I'm going to need to pull it up again. So don't mind me as I quick Google something here. We're going to Google standing wave simulation. Huzzah! And now my Chromebook really is just running tragically slowly today. It probably needs a little bit of help. Okay, but here we go to this standing wave simulation. This one is just very, very lovely. Okay, here we go. Perfect. Okay. Here's what's going to happen when we get a standing wave. Here are all the conditions that have to happen. What you have is you're going to have a wave that starts here, and I'll pause it as it goes, but you're going to have a wave that starts here, and it's going to start traveling across this little rope here, traveling on its journey. Now, as it travels, this wave is going to hit this end right here, and when it hits this end, it's going to reflect. This, you can see, is a fixed end, so it's going to reflect back inverted. What happens with a standing wave is that you get a wave that interferes with its own reflected wave. So you're going to see this red wave right here is the incident wave. It's going to get to here, then its reflection is going to start traveling back the other direction. So you're going to have the incident wave coming in, the reflected wave coming back, and those two waves are going to constructively interfere and destructively interfere at other places. Now, to create a standing wave, and I'll show you what it looks like, but to create a standing wave, you have to have this incoming wave come in at a very specific frequency. If it's not at this very, very perfect frequency, it doesn't work. So it has to be at a very specific frequency, but I'll show you the wave that results. Let's see what happens here. It goes in, hits the barrier, and comes back reflected. Now, the wave that you see, that's the little black wave, that is the standing wave that results from the constructive and destructive interference of the incident wave and the reflected wave. Notice at those places where the incident wave and the reflected wave are totally overlapped with each other and you have complete constructive interference, this standing wave has its maximum points there. If I can show you, let's get rid of the reflecting wave and get rid of the incident wave. What you'll see is all standing waves look like this. They oscillate around these specific nodes here. Here are the node points that they're oscillating around. The nodes stay still. Meanwhile, they have these other regions right here that jump up and down like jump ropes. Again, this wave, this type of wave where you have these like middle parts that are moving, but then these like really weird parts of the wave that are just sitting perfectly still. This standing wave is a result of an incident wave that interferes with its reflection. You can see here that at these points here where you have these big peaks, that's right where the waves line up. Then at these places right here, that's right where the waves line up destructively. So here you have crests lining up with crests. Right here at this point, you can see you have crests lining up with troughs. Going back over here, let's go ahead and pause this thing. Pause. And back to here. A standing wave. Here are the parts of a standing wave that you need to know. A standing wave looks sort of like this. You have a wave. Then you have this wave actually has like these weird points on it, and at these weird points the wave is like weirdly like not moving at all. Then that wave is going to oscillate back and forth at each of these weird little loops. So that loop is going to go up and down between those 2 points. This loop is going to go up and down between these 2 points. This loop is going to go up and down between these 2 points. The places where the standing wave is going perfectly like not going, like the places where it's not moving at all, those are the result of complete destructive interference at these points. And we call these points nodes. They are places of complete destructive interference where the wave is not moving at all. Then we have other places on this wave. Yellow feels like a scary color to use because who can even read yellow? Let's try purple. We have these other places here, like this place and this place and this place, where the wave seems to be moving like crazy. These are what we call antinodes, or sometimes we call them loops. Loops or antinodes are a result of constructive interference. It's that place where the incident wave is interacting with its reflected wave to create some constructive interference to make this thing bounce up and down. Again, the nodes are places of destructive interference. And that's a standing wave, a very specific case of constructive and destructive interference. Well, hey, today we've talked about quite a few things. We've talked about, wait for it, wave transmission, wave reflection, and wave interference. Wave transmission happens when a wave moves from one medium into another. We see that the speed can change and the wavelength can change, but the frequency always stays the same. Wave reflection happens when a wave hits an end, either a fixed end where it reflects back inverted or a free end where it reflects back upright. We've also seen that waves can interfere with each other, and if they interfere with each other, according to the superposition principle, in a way where you have crests lined up with crests or troughs lined up with troughs, then we get constructive interference. But if they interact with each other in a way where you get crests lined up with troughs and troughs lined up with crests, we call that destructive interference. Then lastly, we talked about a standing wave, which is a very, very specific example of constructive and destructive interference, when a wave interacts with its own reflection. And that, ladies and gentlemen, is everything we have on waves for today. I hope you have a wonderful rest of your day, and hope to see you soon. Bye, guys.